Hello, everyone. Welcome to another Flan Talk. Today we have Jiaoda. He's a PhD student at ETH Zurich. He's been interested in transformers, language models, and formal methods, and today he's going to tell us about his current work. Thanks, Jiaoda.
Thanks, Sandy. So, the title of this talk is Characterizing the Expressivity of Transformer Language Models. So the first question would be like, what transformers, right? And this is a follow-up to the work of many of you here. But the most related work is the Yang et al. 2024, which shows the transformer under certain assumptions are equivalent to linear temporal logic. And specifically, the assumed transformers have fixed precision, unique high attention, strict fixture masking, and no position encodings. And we basically follow all the assumptions except the unique high attention part, where we replace it with the more standard softmax attention. And we should also mention the Young and Chen 2024 pretty much investigated the same idealization of transformers. And they show such transformers are upper bounded by C-RASP, which is something they proposed in the paper, but they didn't come up with an exact characterization. And so this is exactly what we're going to establish in this talk. So I will start with some background knowledge on formal languages and formal logic, but I assume most of you are familiar with them, so I'll just go through them very quickly. So an alphabet is just a finite set of symbols denoted as sigma, and a string is a finite sequence of symbols from the alphabet. And the set of all the strings over sigma is denoted by the coding star, sigma star. And a language is just a subset of the sigma star. And we can use regular expressions to describe formal languages, and where we have the symbols from the alphabet, and we have union plus concatenation, the clean star, and the complement. Right. So for example, we can have alphabet star A, alphabet star, which describe all the strings that contain an A. We can also do union, and by plus these two expressions, we can describe strings that contain an A or a B. And we can do the complement of the first expression, which will describe the strings that do not contain an A. So a language is called regular if and only if it can be described by a regular expression. And if this expression do not contain a star, then we call this language star-free. And temporal logic is another tool that can be used to express or describe languages. And so it's called temporal because all the formulas in the logic implicitly depend on a variable representing the time. So when defined over strings, the formulas will just depend on a variable, which means the position in the string. So the formulas are composed of atomic formulas, pi a for every symbol A in the alphabet. So this basically gives you a tool to read the input string. And we have the ordinary Boolean connectives, logical or, logical and not. And we can have also some temporal operators. Here we have past, future, things, and until. If you check out like other definitions in different papers, then the exact operators you have might be different, but as long as you have one of since or until, then they are equally expressive. So the semantics of W, a string W, satisfies a formula psi at the position n, defines it as follows. So if this formula psi is an atomic formula, let's say pi a, then Wn satisfies pi a if and only if the nth symbol in the string W is a. And the Boolean connectives are just defined the conventional way. For example, if you have phi1 or phi2 or psi2, then Wn satisfies it if and only if one of the psi1 or psi2 is satisfied. Yeah, and the temporal operators are defined as follows. So Wn satisfies past psi if there exists a position n before n. So n is the current position, such that Wm satisfies psi. So as long as there's a position before the current one that satisfies psi, it will satisfy its past psi. Right? And similarly for future psi, we need this position to be after the current position n. And Wn satisfies psi1 since psi2 if and only if there exists a position m before n where the psi2 is satisfied and everything between m and n satisfies psi1. And symmetrically, psi1 until psi2 requires this position m to be after n, and everything in between satisfies psi1 as well. So here are some examples. So the string ABB satisfies pi a as the first position because the first letter, the first symbol in the string is a. Right, and as the third position, ABB satisfies past pi a because there exists an a before it. And it also satisfies pi b since pi a because there's an a before the third position. And everything in between, which is just the second position, satisfies pi b. Right? And to define the W without any positions specified satisfies a formula sign, we imagine we are at a position outside the string. So it could be n plus 1, where n is the length of the string, and or it can be 0, which is also outside the string because the first position in the string is 1. Right, so as long as this formula is satisfied at the position outside the string, then we say this string satisfies this formula. And for example, ABB satisfies the formula past A because at a position outside the string, here there is an A before it. Right. And we say the language defined by a formula is a set of strings that satisfy psi. For example, the language defined by past A is just all the strings that contain an A. And if we restrict the temporal operators that's available to the logic, we can get some fragments which are less expressive. For example, if we remove the since and until operators, this will result in something called unary temporal logic. And it's less expressive than the complete one. And in this paper, we introduce a fragment that's even less expressive, which only has the past operators. And we will show this is exactly the expressive power of transformers under our investigation. And so first order logic is something slightly different, but also deeply connected with linear temporal logic. So the only difference here is instead of having only one implicit variable, we can have many variables, x, y, z, etc. And they are also interpreted as positions in the string. And we also have atomic formulas, pi a. This is the same as temporal logic. We also have the connectives. And we don't have the temporal operators, but we have the standard quantifiers, like existential quantifiers and universal quantifiers. And in addition, we also have a binary numerical predicates that can be used to determine the order, the temporal order of different variables. So, so if this formula phi has variables x, y, z, etc., and if W satisfies phi with the variables being associated with the position ij, etc., we will write wij models phi xy. Right, so for example, ABB13 models the formula pi ax and pi by. If we replace x with 1 and y with 3, we can see ABB satisfies this formula because the first symbol is A and the third symbol is B. Right, and if a formula has no free variables, we call it a sentence. And the language defined by a sentence is just the set of strings that satisfy this sentence. So for instance here, this formula says we have an A at x, and we have a B at z, and every y in between x and every y is between x and z. In other words, it defines language that starts with an A and ends with a B, which is just A alphabet star B. So it was known that both first-order logic and intermediate logic are equally expressive, and they both define exactly the star-free languages. And if we restrict the number of distinct variables, we can get, if we restrict it to B2, then we can get FO2. And note that we are restricting the number of distinct variables, not just, so for example, in the previous language, the A alphabet star B, we used 3 variables x, y, z to define the language. But here we can reuse the variable x such that there are only 2 distinct variables, x and y. Right, so this language is also definable by FO2. And it's shown that FO2 and LTL, this unary temporal logic with only past and future operators, are equivalent in expressive power. So in order to define a fragment of FO2 that's equivalent to LTL past, we require the quantifiers in FO2 to behave like past operators. So formally, we require every bounded variable bounded by the quantifiers to be less than the free variable. So for instance, here in the last part of the formula, the existential quantifier, the bounded variable by this existential quantifier x is larger or equal than the free variable here, y. So this cannot be defined by PFO2. Yeah, so basically we introduce PF2 and LTL past, and they are equivalent in expressive powers. So in the following section, we will first show transformers can be translated into PFO2. And then in the second half, we will show LTL paths can be translated into transformers. So because PFO2 and LTL paths are equivalent, we hereby establish the equivalence between LTL paths and transformers. So before we start, we assume fixed precision, which means we have a finite countable set of all the values that a number can take in the transformer. So in a very simple case, we can imagine the set is just -1, 0, or 1, with 2 special numbers of values, negative infinity and positive infinity. And before a string is fed into the transformer, we append an EOS token to the end. So we denote W bar as the W appended with an EOS, and alphabet bar is just the alphabet with an EOS token. So because we ignore position encodings, so in the input layer, we just apply an embedding function to every symbol in the string. Right, and this embedding function just converts a symbol into a vector of dimension d. So this can be simulated by PFO2 very easily, just using the atomic formulas. Again, we consider a very simple case here. We assume that d equals to 1. And the set is this small set we mentioned. And the alphabet has only two letters, A and B. And the embedding function converts A to 1 and B to 0, as well as EOS. So we can simulate this embedding layer as follows. So EI is equal to 1 if and only if the symbol at ith position is A, right? Because only A has an embedding 1. Otherwise, it would be 0, right? And so the next component we consider is the feed-forward layer, which is just a function of this type. And as long as it's deterministic and we have like finite input space and finite output space, we can just enumerate all the possible inputs and all the possible outputs. For example, if we assume the input to the feed-forward layer is the embedding, right? It's just the thing we just showed. And this feed-forward layer just computes this very simple function that multiplies the input by -1 and then adds it by 1. Then we can simulate this feed-forward layer as follows. So f will be 0 if e is 1, right? -1 plus 1 is 0. And so combining this with the simulation we had in the previous layer, we get f equals to 0 if and only if the position at I is A. Right, and similarly, we can simulate f equals to 1. And other functions in the transformers can be simulated in the similar way. So this includes the projection in the attention layers and the exponential function, the square root function, the residual connection, their normalization, and even the final length modeling head and the classification head. So as long as the function is deterministic and you have finite input space, finite output space, you can always just enumerate all the possible outcomes. And something slightly different is the pairwise compatibility score. It's different because it depends on two positions, I and J, rather than just one. But this can also be simulated because PFO2 allows two distinct variables. For example, if both the query and key are just the embedding, then S will be equal to 1 if and only if both positions I and J have an A, because only A has non-zero values, right? So here comes the most difficult part, which is the summation in the attention layers. There are two sums. The first is in the denominator of the softmax, and the second is the weighted sum of the values, right? And the reason why it's hard is summation typically requires counting quantifiers to simulate, and that's why previous works, they all use some sort of counting ability, such as like TC0 or just counting quantifiers to simulate the softmax attention or even like average Harder attention. And without counting quantifiers, PFO2 cannot count. However, what it can do is count up to a threshold. So we will illustrate this with some examples. The standard existential quantifier just means existing no less than 1, right? And we can define existing no less than 2 just by cascading two existential quantifiers. And by combining existing no less than 1 and existing no less than 2, we can define existing exactly 1. Right, and more counting quantifiers can be defined in the same fashion up to a threshold. So let's go back to examine the first sum in the softmax. So note this is a sum of exps, and because the output of exponential function is always positive or non-negative because we have negative infinity. But this means this is a sum of non-negative values. And this makes it simulatable by PFO2. And the reason is, again, we assume the non-negative values are 0, 1, and infinity. So there are only three possible outcomes, 0, 1, and infinity. And the sum will equal 0 if there does not exist any 1 or infinity before the current position.
Hey, Jiaoda, there was a question in the chat of how
Mhm.
you define exponentiation in softmax under finite precision.
So we didn't like specify how like rounding or uh, like the operation is performed. We just, as long as it's deterministic, which means for an input there is a deterministic output, then we'll be able to simulate it. Right.
Yeah, what I was wondering because exponentiation is like an operation that can potentially blow up. So I was wondering how you deal with this. I know usually like in other papers they assume something like that an output is bounded in the same way such that you can't have more bits to express your output than input. So I suppose you have to like manage overflow potentially, right?
Right. So we didn't consider that. If it overflows, then it doesn't matter. Like we can let it overflow.
Okay, thanks.
Yeah. Thanks for the question. Um, yep. So let's go back to the first summation. So because it's a sum of non-negative values, we can simulate it with threshold counting because there are only three possible outcomes, and it's 0 if there's no 1 or infinity before it, and it's 1 if there exists only 1 before it, and there's no infinity. And if it's infinity, if there exists two, more than two ones, or there exists an infinity, right? So we can just enumerate all the possible outcomes and use threshold counting to simulate it. Now we look at the second sum, which is different because it's a sum of the value matrices, and value can contain both positive and negative numbers. However, um, note that the attention weights computed by softmax will lead to a 0 if the denominator is an infinity, right? So this means the attention weights can only have a finite number of non-zero entries. And this is also something pointed out by Will's paper on the T0 low precision transformers. The fixed precision transformers can only attend to a finite number of positions, right? So this means this sum here is a sum of a finite number of values, which can be simulated by threshold counting as well. And the threshold would just be the maximum number of non-zero positions. Yeah, so that's the last piece in the transformers that we need to simulate. And do we have any questions?
There was a comment in the chat. Um,
Just a really minor one. So in that last slide, do you mean that there's a fixed upper bound on the number of values, non-zero values in the
Yeah,
denominator?
exactly.
Sorry?
Yes.
Okay, thanks.
Yeah, this should be bounded number of values. Okay, so we move on to the second half where we show how transformers can simulate formulas in LTL fast. And intuitively, we just assign each formula to a distinct dimension in the transformers. And we use 1 to represent true and 0 to represent false. So first, we simulate the atomic formulas. We imagine we have a map G that maps each distinct symbol to a distinct index D. And so this this embedding E or H0 DI will be 1 if and only if the dimension corresponds to the symbol at this I position, right? And because biases are sometimes omitted in the attention layers, we designate dimension dB to always be 1. And so this is most clear if we give an example. So assume the input string is ABB or AAB. And so this is the string with EOS. And imagine we have 5 dimensions. The first dimension corresponds to the pi A, and the second one corresponds to pi B. The third corresponds to pi EOS, and D prime is an unused dimension at this time, and dB is the bias dimension. So as you can see, the first embedding is only 1 if and only if the symbol at this position is A, and B is 1 if it's B. Right? And we can simulate connectives. Imagine psi1 and psi2 are simulated by D1 and D2 respectively. We can construct a layer to compute the not psi1 with this simple linear layer. And we can simulate psi1 and psi2 with this layer with a residual activation function. And for example, if psi is not pi A, then we can just revert the first dimension and then store it in the unused dimension D prime. Yeah, and now we show how to simulate the parse operator. Assume, again, psi1 is simulated by D1. And the formula we're interested in is psi equals parsed psi1. And so intuitively, we just want the attention to attend to the positions where psi1 is satisfied, or D1 is 1. So this means we need the score function, the score matrices, to be negative infinity. Sorry. Is there a question? Yeah, we require the score to be negative infinity if the D1 is 0. So this means you only attend to the positions that we care about. And yeah, for example, the phi is past pi A, then we will set the projection matrix for the query to be like this. So we first go to the dimensions that we're interested in, which is pi A, the first dimension, and then we set the dB to be positive infinity. And if we multiply it with the input, the edge, then we will end up with this query matrix, which is infinity in the first dimension and 0 everywhere else. Yeah. And for the key matrix, we just want it to be edge minus 1, edge is input. And this can be achieved by having a matrix like this. It's basically an identity matrix with the last column being subtracted by 1. So if we multiply this Q with K, then we will get this score matrix, which is negative infinity everywhere the symbol is not A and A. Yep. And if we compute the softmax, then factorizing the strict future masking, then we will end up with these attention weights. And then we do the weighted sum of values, we will end up with the correct past pi A. Yep. However, there's an issue. As we just said, under fixed precision, a bounded number of positions can be attended to, right? So if there are too many positions that satisfy psi 1, so in the example we just showed, if there are too many positions with symbol A, then the attention weights will be zeroed out. So to circumvent this issue, we implement a second attention layer that simulates past psi 1, which means it attends to the positions where the first layer has a value 1. And so this past psi 1 will also always be correct. And then we take the logical OR between the flawed first attention, the flawed past psi 1, and the past psi 1. You will end up with a correct past psi 1. So again, we show this example. So we assume the maximum number of positions that we can attend to is just 1. So in the first layer, the past pi A, in the first position, there is no A before it, right? We have strict future masking, so there's no A before it, it's 0. And in the second position, there's an A before it, so it's 1. But in the third position, there are 2 A before this B, which means it exceeds the maximum number of positions. So the attention weights will be 0 out, so it's an 0. And the same goes for the EOS token. So the results dimension would be like this. And then we implement a past pi A, which attend to positions where the first row is 1. Right, so in the first position, there's no 1 before it, so it's 0. In the second position, it's still 0. But in the third position, there is an A here before the current position, so it's a 1. And in the last position, it's also a 1. So if we take the logical OR between the first two dimensions, it will just be 0, 1, 1, 1, which is the correct past pi, right? Because the first position has no A before it, and all the subsequent positions have an A before it. So this is a very convoluted way to construct the pass operator, which I'm pretty sure is not the way transformers implement in practice. But anyway, we somehow able to get rid of the fixed precision constraint. And so we establish the equivalence between transformers and LTO past. Yep. So the question follows is what are the exact expressive power of LTO past? It's not interesting if this is just something we come up with and no one understands it. But we managed to prove that it's equivalent to a quite well-studied class of languages called left deterministic polynomials. And they are equivalent to R trivial monoids and partially ordered DFA, deterministic final automata. And due to time constraint, I'm not going to introduce the definitions for these two, but I will briefly discuss the partially ordered DFA. So a DFA is just a Phi tuple with an alphabet and a set of states, and initial states, and a set of final states, and a transition function. And a DFA is said to be partially ordered if there is a partial order on the states. And in plain language, it means once you leave a state, you can never return to this state. And we proved that for such a partially ordered DFA, for every state Q, we can write a formula in LTL past psi Q such that this psi Q is satisfied by a string at the position n if and only if the DFA is in state Q upon reading this prefix up to n. So this means we can determine which state this DFA is in with a formula, right? And combining this with our previous results that every formula in LTL path can be simulated by transformers. This means we have a dimension for each state in the DFA, and it's one if and only if the transformer is in this state, right? And so we can basically simulate partial ordered transformers with partial ordered DFA with transformer language models rather than just transformer recognizers. So we can just implement a language modeling head that maps each state to the symbols that are permitted at this state. Right, so as obviously we have some outgoing edges and where the certain symbols are permitted, and we will only allow these symbols to have non-negative infinity values. So this is how, but this still have some sense of like Boolean because we cannot represent the exact weights. So the DFA is still unweighted, but we can easily extend it to weighted DFA as long as the weights is a valid semi-ring. Yeah, so that's all for the theoretical part. And our paper also has a experimental section where we basically handpick a bunch of languages that, according to our theory, can or cannot be recognized by transformers. So the languages that cannot be recognized by transformers according to our theory includes some counter languages such as AMBN and parity, and DIC12, which is the bounded DIC language with a pair of parentheses and limited to -2. Also DIC11, which is just AB star, right? And locally testable language such as alpha beta, AB, alpha beta. So anything that contains AB as a substring. Also RDP, which is right deterministic polynomial, which is something symmetric to LDP but cannot be recognized by transformers. And the last, which is anything that ends with a symbol B. So these are all languages that are very simple, and some of them have been shown that fall within the capacity of transformers under different assumptions. And in contrast, the languages that can be recognized include the left deterministic polynomials and piecewise testable. So this requires a certain subsequence to exist in the strings rather than a contiguous substring. And also the first language, which is the language that starts with a symbol B. And so here are the results. The bottom line is our experimental results align pretty much perfectly with our theoretical predictions. So under this line are all the languages that we predict the transformers can recognize. And we see they do obtain 100% accuracy at maximum. And this is a length generalization setting. So we train on 1 to 40 and test on 41 to 500. This is the setting we took from the Dilettante's paper and Alexandra's paper. And for everything above this line, so the languages that we predict transformers cannot recognize, they do kind of fall short, right? They cannot obtain perfect accuracy. So yeah, and we also implement LSTM to make sure that all the languages are learnable given the data we created. Yeah, we also did some experiments on language modeling. and we visualize the internal representations that correspond to different states in the partial order DFA. And so for LDP, the left deterministic polynomials, we show the internal representations are linearly separable for different states. But for RDP, the kind of mixed up together. That's all for my presentation.